Suppose we have a function f of x, which in this case is the square root of x, and we take the integral from x is equal to the x value of a to x is equal to the x value of b, and we get this figure right here. Now imagine further that we take this shape and we rotate it completely around the x-axis. So it would look something like this as we rotated it around. And we would end up getting a three-dimensional solid. And what we're going to do is try to figure out how to calculate the volume of that solid. So to start, we're going to go back to when we estimated the integral using the Riemann sums, as we can see here, and we'll get a better and better estimate of the integral as the number of rectangles increases. Well, we can do the same thing with the solid by looking at what happens if we take each of these rectangles and rotate them, creating a series of disks. Each disk is a small cylinder, and the width of that cylinder, or the height, will be just the width of each one of these rectangles. The surface area, or the area of the base, will be just equal to the area of a circle with a radius equal to the height of this rectangle. So for example, right here, this first cylinder, we could see that the height of, or the radius of the circle is just equal to the value of the function at that x point right here. So here the radius of this cylinder is equal to 1. So its volume, or its base area, is going to be equal to pi r squared, or pi times 1 squared. And its volume then will be equal to pi r times the width of this, which is about 1. So the volume would be about pi r units cubed. And what we see is that the volume of the solid created when we rotate the integral around here is equal to 98.96 cubic units. Now let's take a look at the estimates when we rotate the disks. Well, right now with 8 disks we get a volume of 89.34, and not surprisingly, as we increase the number of disks, our estimate gets closer and closer. And so the volume of this figure then, just as was the case with the area under the curve, is equal to the limit of the volume of the sum of the volume of those disks as the number of disks approaches infinity. And so that gives us a means for calculating the volume of a solid rotated around the x-axis like this. Now, we could also rotate this thing around the y-axis, and we would get a different series of disks. And let's take a look at what that would be. And now the width of each, or the radius of each cylinder, is no longer the x value, but is equal to the, no longer equal to the y value of the function at that point. It's equal to the x value of the function at that given point. And we'll spend a lot more time with that later. But for now, we'll be working with what happens when we rotate a figure like this around the x-axis, and thinking about what are the dimensions of each of these cylinders, and then thinking about how to create an integral expression out of that.